One of the ways that we master the vocabulary and concepts of engineering systems analysis is to work out example problems. So we're going to return to our book by Ravel, Whitlatch, and Wright and take a look at the chapter on graphical solutions. Any one of these problems from problem 1 to 13 at the end of the chapter will do. But for the purposes of this example, I'm going to focus on problem number 12. I've copied the aspects of the problem over onto our sheet of paper so that we can take a look at the objective function and the constraints. Keep in mind that the objective function is represented as z, and we want to maximize it. And we have 1, 2, 3, 4, 5, 6 constraint equations. They're all expressed as inequalities. They include the positivity constraints and 2 balance constraints that combine in this linear way functions of both x1 and x2. Because it's a chapter on graphical solutions, it behooves us to draw a graph. I recommend you work this out for yourself on graph paper, but for right now, I'm going to sketch an approximate solution without the benefit of graph paper, and we'll see how well I do. We want to put each one of these constraints on the graph, and I've started with the positivity constraints by focusing on the upper right-hand quadrant of our Cartesian plane. This is where x1 must be positive and x2 must be positive. So I'm drawing these arrows to indicate on which side of these inequalities, x1 greater than 0, x2 greater than or equal to 0, the feasible region for just these positivity constraints lies. Now let's plot the easy ones. x2 must be greater than or equal to 2. And that looks like this. I've dashed it because we don't know whether this is an active constraint or an inactive constraint yet. But it's x2 is greater than or equal to 2, and so we have to be on the top side, the x2 positive side of this constraint equation. Now let's do x1 must be greater than or equal to 5. 1, 2, 3, 4, 5. x1 greater than or equal to 5. And again, we have to be on the right-hand side, the positivity side of this equation. We can see the feasible region is getting narrower as we add constraints. The next two, the balance constraints, are a little less straightforward. We have to do sort of a little algebra, and we're going to solve them by setting one of our parameters equal to 0. We're going to plot 2 intercepts, and then we'll connect those intercepts with a straight line so that we can plot these constraints. Let's start with the bottom one. x1 plus 2, 5x1 plus 2x2 must be less than or equal to 30. When x2 is 0, x1 must be less than or equal to 6. When x1 is 0, x2 must be less than or equal to 15. Well, I'm out of room. I can't even have the space to draw the 15, so we're going to approximate it. One of the complications of not having the graph paper is I don't understand the details of what's going on in here. I'm just hand sketching it, and we can't rely upon what appears to be an intersection point, although we could test for that. When x2 is 2 and x1 is 5, we get 25 plus 4 is less than or equal to 30. So what that tells us is that this point is less than or equal to. Here's our constraint equation. 5x1 plus 2x2 must be less than or equal to 30. The next question is, on what side of this constraint equation does the less than or equal to sign put us? Let me show you how we're going to work that out. Because it's less than or equal to, and our term for x1 is positive, we have to be on the negative side of x1. And same thing is true for x2. We must be downward or on the negative side of x2, and that means the feasible region is going to be in this direction, to the lower left. That might suggest that there is a tiny little feasible region that satisfies the x1 greater than or equal to 5, the x2 greater than or equal to 2, and the 5x1 plus 2x2 less than or equal to 30 right in here. But we have one more constraint equation to plot. When x1 equals 0, x2 must be, watch the negative sign, we have to be greater than 30, negative 5. That intercept goes right here. And when x2 is 0, x1 must be 6. So the constraint equation looks like this. And that's 5x1 minus 6x2 is greater than or equal to 30. On which side of the constraint equation must we be? Let's take a look. It's greater than or equal to 30, so we're on the positivity side of x1. Greater than or equal to 30 puts us on the negativity side of x2. And so the direction of this line on which the feasible region would lie is down and to the right. Now we can see that we have an unbounded problem. That is, there is no, this is going to be a little tricky. Without this constraint, we could imagine a feasible region that satisfies this one, this one, this one, and it would be unbounded. That is, there's sort of this open area in which really large values of x1 and x2 going all the way to infinity would satisfy all the constraints, except for this problem, this constraint. So it's not really unbounded. It has this quality of being unbounded until we consider this constraint, that we must be less than or equal to 30. Remember I said that the first three constraints we plotted might create a tiny little space in here that is feasible. But once we've plotted this last constraint and we find that we must be down and to the right, we find that what was feasible has become infeasible. So this problem is over-constrained, which is kind of the opposite of unbounded. There is no feasible region. That means there's no feasible solution that satisfies all of the constraint equations. We needn't even concern ourselves with the objective function because there's no solution that we can make work. If we were going to concern ourselves with the objective function, there's a way to plot it that might be informative anyway. One of the things that I do with the objective function, I'm going to change colors to blue to do this, is plot what are called contour lines. If this were a topographic map, they would be contour lines. A fancier way of saying it is these isometric lines, lines that satisfy the objective function at different values. For example, suppose x1 equals 0 and x2 equals 0. Then we would find that z equals 0. We could create all the other combinations of x1 and x2 that satisfy the equation z equals 0. But we're going to do something a little bit more interesting than that. Suppose that we take a value like 5 for x1, 2 for x2. Here we have 50 plus 8. That's z right here equals 58. Which other combinations of x1 and x2 amount to z equals 58? We can solve for that by saying z equals 58 equals, and now we're going to choose one of these intercepts. x1, for example, x2, for example, could be 0. So we'll choose 10 x1 plus 0, and we find that x1 must equal 5.8 for this z equals 58 contour line. What does that look like? That's about here. All points that satisfy the z equals 58 line would go in this third dimension. This is sort of the objective function elevation of z equals 58. We could choose a different combination. We could choose, for example, let's take 6 and 1, 2, 3, 4. x1 equals 6 and x2 equals 4. That would be 60 plus 16 is 76. So this value, 6, 2, 3, boom, that's z equals 76. And we might ask ourselves, what are all the combinations of x1 and x2 that results in z equals 76? Again, let's choose x2 equal to 0, and we will find that x1 must be 7.6. And where does that show up? Right about here. Because this is a linear problem, all of our isometric z lines, this one, z equals 76, will be parallel to one another. Remember, we want to maximize z, and both terms in the objective function, x1 and x2, are positive. What that leads us to believe is that z will always be increasing with x1 and x2 increasing. The max z will be found up and to the right. As these constraints are plotted, we don't have any extreme points which bound what would have been a feasible region if there was one. We don't have any extreme points that would bound this max z. We're going uphill, that is increasing z as we go up and to the right. The only constraint that we have is this one. The 5x1 plus 2x2 must be less than or equal to 30. And that prevents us from choosing values of x1 and x2 that are too large. What I've done now is I've shown how to plot in this pseudo third dimension the value of the objective function, and intuitively look in the direction of increasing for maximization or decreasing for minimization objective function to find those extreme points that might represent the solution to a linear problem. What's an extreme point? Where two constraints are equal. That is, where they intersect. It's possible to have an extreme point, but it's only meaningful as an extreme point if it represents a feasible solution. In this problem, we have no feasible region. We've only plotted the objective function for the academic purposes of illustrating how the objective function results in parallel lines. Although there are some candidates that we could test for the extreme point because they represent intersections of the constraints satisfied as equalities, there are no extreme points because there's no feasible solution. In any linear problem, if there is a solution, it will be found at an extreme point. And I'll leave you to comment on the video to explain to me why.